So this video is about the gravitational field strength. So in those of you who are familiar with the Newton's law, you might have used an equation F equal to ma. Say for instance, if an object is falling, so that object that's falling from, say for instance, 50 meters above the Earth's surface. To calculate the force, what we do is we multiply the mass with the acceleration. We call it the gravitational acceleration. The value that we normally use is 9.8. So in the previous video that we discussed about the universal gravitational force, that's the force acts between two masses, two objects. Like in this case that we have got a mass. This one is m and this one is m. So as we discussed previously, the force between this mass and this mass, we can put it as G is equal to G m over r squared. Okay, so the gravitational field strength, that's why here gravitational field strength is defined as a force acting on 1 unit of mass. So in this case, we are talking about 1 kilogram of mass. So if we write it down here, so the force acting between those two masses equal to G m over r squared. And we are defining that the gravitational field strength is F over m, because we want to find the force acting on 1 kilogram of mass. So we remove this m, so that will become Gm over r squared. So that's what we call gravitational field strength. And so we call it G. So this G is a variable, so it's not a constant as we normally use it for situations where we are dealing with height, low heights. So the equation for the gravitational field strength is G is equal to Gm over r squared. It's always good to memorize it, even though that they give it in your exam sheet. It's always good to memorize this equation and also figure out how you derive it. So to derive that, all that you're using is that you're using this equation, the universal gravitational force, which is the Newton's law, F is equal to G times m over r squared. And then you divide the force by the mass and you get this equation Gm over r squared, which is equal to Gm over r squared. So if we draw a graph for the gravitational field strength, here. So if we use the x-axis for the radius and the y-axis for the gravitational field strength, and say for instance this is the radius of Earth. So what would happen is that at this point we know this is 9.8 at this point, but after that, as the radius increases, the gravitational strength is going to be reduced. So, but in the simple situations, what we do is that we use the gravitational strength as 9.8, and this is the radius. And something that you need to make sure is that the radius is from the center of the planet Earth or any mass that this is orbiting around. That radius is from the center to the point where we have the other mass. So in case that if they give you the altitude from the surface of the Earth to here, then you need to add the radius of the Earth plus the altitude. So in this case, that say for instance they give you this one as R and this one as H. In this case, R is equal to R plus H. Okay, let's work on few examples to understand these things better. The previous one, in this place, this is a planet, and these are the lines with different radius. Say for instance, this is radius R1 and this is R2. And if you use this equation to find the gravitational field strength at this point and this point, and you will find that at this point, the gravitational field strength is less than this one because the radius here is greater than the radius here. Something else that we need to know, that if we have two planets, planet A and planet B, and the mass is different and the radius is different. So the gravitational field strength for the planet A and planet B will be different because our equation says that the gravitational field strength is equal to Gm over R squared. Because M is different, R is different. So if this is Earth and if it's another planet, Saturn or another planet, and obviously the gravitational field strength or gravitational acceleration is going to be different. So let's do an example that uses this equation for different planets so we can compare the gravitational acceleration. And the second thing, we also need to know that the weight of any mass is given by W is equal to mg. So for instance, if you have 2 kilograms on Earth and the weight is given by 2 times 9.8 because we use the gravitational acceleration is 9.8, and so if the same thing that we are going to weigh in another planet, that will be 2 times and whatever the gravitational acceleration in that planet P. So let's use that to solve a few problems. So here we got 2 planets, and they both have different masses. The first one is M, and the second one is 4m. So this is M, this is 4m. And also it's given that this point, the gravitational acceleration is 4. So what we have got is that this is, we got the gravitational acceleration at this point due to this planet. And what we are asked to find is the acceleration at this point due to the planet X at the same distance d. So what we know is that the distance from the center of the planets is the same, d here and d here. So let's use the formula that we discussed before, which is the gravitational acceleration or gravitational field strength is equal to, we have to use small g for that, is equal to Gm over R squared. So planet X, if we use the same thing, Gx is equal to Gm over d squared. And for this one, Gy is equal to G, we got 4m. So what we do is we put the 4 at the front, 4Gm over d squared. So we were given that Gy is equal to 4, right? That is basically equal to Gy. So this is equation 1, equation 2, and if you divide equation 1 by 2, we get Gx over Gy is equal to, we divide that by that is basically gm over 4gm, because what will happen is that the d squared will be cancelled out by this d squared, so we end up with this one. So gx over gy is equal to 1/4. So gx is same as gy over 4, which is 4 over 4, and the answer is 1 meter second minus 2. So there's not much space there, so let me write it down here this side. So we found out that gx is equal to gy over 4, which is 4 over 4, which is 1 meter is minus 2. So I mean, from the results, that what we see is here, this is a big planet, and this is a smaller planet. This is a big planet, and the big planet that we got, the mass is 4m, and this here the mass is small m, and the gravitational acceleration at this point is 4, and we find out that for smaller mass, the value of acceleration is smaller. And this equation will tell us what that value is. So many problems that you will be solving to find the gravitational acceleration, or they use the word gravitational field strength, is all about using this formula. And what we know is that it depends, so it's proportional to the mass and inversely proportional to the square of the radius. So if the mass increases, the gravitational field strength increases, and if the radius increases, and the gravitational field strength decreases. So let's look at the. So this is an example of about weight in different planets, and it's given that in Mercury that the gravitational acceleration is 3.6, and we know it's 9.8 on Earth. So 9.8. So they're asking us to find the weight. So if the weight, because they have given the mass as 2 kilograms, so weight here is going to be W is equal to mg. So that's the equation we're going to use. So W is equal to mass in 2 times 9.8, and here the weight is equal to mass is the same. I mean, that's what we need to remember. The mass is the same no matter which planets you go to, but the only thing that's going to differ is the gravitational acceleration. So in this case, it's going to be 3.6. So you will get 9.8. It's the 19.6 here, and this one will be 7.2.